So one of the main tools we're going to be using over the remainder of the year is this tool of the line integral. And this is just another way to add things up. But in this case, rather than like in BC calculus, adding things up over some interval in x, or even a double integral where we add things up over a region, now what we're doing is we are integrating over some curve. So here we have a curve in the xy plane. We're going to start in 2D. And we're just going to describe this curve C. And as you might remember, way back when, we have a bunch of ways to describe that curve, right? One is that we could describe it as a vector function, r of t, where we have, component functions x of t and y of t. We could also do so parametrically, where we're just like, oh, x equals some function of t and y equals some function of t. And we played around with these a lot and found that they were functionally equivalent. So let's say we have some curve, and what we want to do is we want to add up at every point on that curve the value of some function. In this case, we're going to start by describing these for some scalar function. Some scalar function f. So what we want to do is we want to be able to come to some point on the curve and ask what's the value of that function f of xy, and then do so at another point, and kind of add it up, all the way around. Well, anytime we want to do an integral like this, we have to cut things up. And so what we're actually going to do is we're going to cut up our interval in time, in our parameter t. So we're going to slice our parameter t. And here t goes from a to b. And so let's just say that this is, we start at r of a and we go up to r of b. We're going to slice up that parameter into little elements dt. And as we take each step dt, that also kind of cuts our curve up, but it's not necessarily going to do so evenly, right? At some places we might be moving faster along the curve, some places slower. So the relationship between dt and these little segments, which I'm going to call ds, is not, they're not the same. dt and ds are not necessarily the same. And then what we're going to do is we're going to take our integral. And one physical interpretation of this integral is that if you kind of imagine the function being some height, we're sort of adding up the surface area of some ribbon. We're kind of doing a traditional Riemann sum, right? That like, here's our traditional Riemann sum. And we're wrapping it on the curve. Well, in that case, what do I need to put into my integral? Let me take one of these little segments here. It's got a base of ds, which is whatever one of these little bits of arc length is, and a height of f. So when we're doing these integrals, what we write is we write these integrals this way. We write them as the integral over our curve of f ds. Now, this is a little bit hard typically to do, parameterizing things in terms of arc length. So we're going to cast our mind all the way back and remember that we actually knew way back in chapter 13 what this little ds element was, and it was the square root of dx dt squared plus dy dt squared dt, or in fact just, if you prefer, the magnitude of r prime times dt. So we will most often actually integrate these this way. We'll actually almost always do them in terms of t. So what we'll actually do is we'll convert f into a function of our parameter t by making appropriate substitutions. And then we'll get our little square rooty term, dx dt squared plus dy dt squared dt. So we're almost always going to do these integrals dt. At that point, that's actually enough information for you to start solving these integrals. And at this point, we've done a couple of them in class as well. If you run into a case where your curve is not smooth, by the way, where your curve has some jagged corners and different segments, what you can do is you can just split it up into a variety of different curves, and then you can do, the integral over c1 plus the integral over c2 plus the integral over c3 and add them up that way. The second type of integral that I want to discuss, though, is actually the integral of a vector field. So we're going to shift our attention a little bit. We're going to keep this in mind. But I want you to imagine instead that we are moving through a space that has some vector field f in it. And I'm just going to draw a couple of those vectors, right? So I don't know, here's our vector field, f. And we are moving along a path through that space. Once again, we're moving along a curve C through that space. And I want to kind of know, what is the influence of that vector field? If I imagine that vector field as a force pushing me along or pulling me in different directions, is that force accelerating me along my path? Is it fighting me as I'm moving along that path? What is the influence of that vector field? And specifically, we're interested in the amount of the vector field that goes in the direction that goes parallel to our curve. So what we're going to do is we're going to do the same splitting up dt, and we're going to get the same little divisions on our curve ds. So just like before, we're going to parameterize our curve. We're going to get some divisions dt and a division ds. And in these little divisions, what we're going to do is I'm going to say, I want to know how much of my vector field, so let's say I'm here in this little ds, right? My vector field maybe points this way. Well, what I actually want is I want the component of my vector field that goes in the direction of motion, that's parallel to my path. So fortunately, we have ready and waiting for us a tool that lets us find that out, which is the dot product. The dot product tells us how much two vectors are in the same direction. And we conveniently already have a vector that points in our direction of motion. This is the unit tangent vector, which you might remember is for a path r, is r prime turned into a unit vector by dividing it by the magnitude of r prime, and that's t hat. So for these vector line integrals, for these vector field line integrals, we often write them this way. We often write them as the integral over c of whatever our vector field is, dotted with our unit tangent vector ds, f dot t ds. Now, this is a very intuitive way to do it. I've just explained why we do f dot t, because that's the component of f in our direction. So we're going to add up the components of f as we go along. In practice, though, these again are not great to do. So let's see if we can convert them into an easier dt integral like before. And so what we're going to do is we're going to remind ourselves that this is a vector field f dotted with, okay, unit tangent vector is r prime over the magnitude of r prime. But we remember that ds is itself the magnitude of r prime dt. So a serendipitous thing happens with our vector line integrals where that square root term cancels out. And so what we actually end up with for vector line integrals is just f dotted with r prime dt. F dotted with r prime dt. And this is a common way we will do these integrals. There's actually another way we will write them, though, that's even more straightforward. You might recall that we often write our vector fields in the form pi plus qj, right, where these are our component functions p and q. And I can also think that, r prime, I can also imagine here that r prime is sort of like, dx dt I hat plus dy dt j hat. So I can rewrite this integral in a slightly different way, which is this, as the integral of p dx over dt plus q dy over dt. That's me doing the dot product. And you'll notice I get a lot of dx dt dt, dy dt dt. So we actually write this in a really cute and compact form, which is as the integral over our curve of p dx plus q dy. P dx plus q dy. I'm running out of ink. P dx plus q dy. Whoa. No, I'm not running out of ink anymore. P dx plus q dy. And so remembering here that when we write dx, what we really mean is, kind of x prime dt and dy is y prime dt. So we'll do some more examples of that in class. But this is also a common way that we will evaluate these integrals. And we'll see that formation, the p dx plus q dy, become more and more important and pop up in more and more theorems as we go along.